Okay, so let's talk about set theory today. I will show this fantastic result about intersection of sets and the difference of sets. As you know, the intersection tells me which elements belong to both sets, and the difference given by this symbol tells me what elements belong to this set but not this set. I will prove this proposition that says that if I take the intersection of two sets A and B first, and then I remove the elements of C, I will end up with the same set in the end as if I remove the elements of C from A, remove the elements of C from B, and take the intersection later, afterwards, of these two sets. Okay? So this is a equal between sets. I will prove that the left-hand side, this is a subset of the right-hand side, this, and then I will prove the other way around. I will prove that this right-hand side is a subset of the left-hand side, this part here. Okay? So the first part, to prove the first part, that the left-hand side is a subset of the right-hand side, I pick a generic element on the left-hand side, pick any arbitrary x here, okay, any one, and I will prove this element must be an element of the red set on the right-hand side, okay? So if x belongs to this, it belongs to this set and does not belong to this. So x belongs to the intersection of A, B and does not belong to C. That's what this statement means. But when x belongs to A and intersection B, that means that x belongs to both A and B. So, and here I'm just repeating that x does not belong to C. Okay? Now, x belongs to A, x does not belong to C, therefore x belongs to A minus C. X belongs to B, x does not belong to C, therefore x belongs to B minus C. And if x belongs to this set and also to this set at the same time, it belongs to the intersection of these two sets. Okay? So what did I do? I started with any generic element of this set here and proved that x must be an element of this set here. Okay? Now let's do the other way around. Let's start with element of this set here. So let x be any arbitrary element of A minus C, intersection with B minus C. Because x belongs to the intersection, x must belong to both this set and this set here. That's why I'm writing here, x belongs to A minus C, and x belongs to B minus C. But by definition of A minus C, when x belongs to A minus C, it means that x belongs to A, and x does not belong to C. When x belongs to B minus C, it means that x belongs to set B, and x does not belong to set C. Okay, so this line we learned that x belongs to A, x belongs to B, and we learned twice that x does not belong to C. Because x belongs to A and x belongs to B, we learned that x belongs to the intersection of A and B. Here I just repeat that x does not belong to C. And finally, because x belongs to the intersection of A and B, but x does not belong to C, then x belongs to in the intersection of A and B minus C, which is exactly my left-hand side. Okay, so we started with a generic element on the right-hand side and proved that every element of this right-hand side must be an element of the left-hand side. Therefore, the right-hand side is a subset of the left-hand side. Okay, so again, in part 1 we learned the left-hand side is a subset of the right. In part 2 we learned that the right is a subset of the left-hand side, and therefore these sets must be equal. In terms of Venn diagrams, let's look at the left-hand side first. I take the intersection of A and B, would be this region, and then I remove C. So I have to remove that. I end up with this region here. On the right-hand side, I first take A minus C, which would be here and here. Then I take B minus C, which would be here and here. And what is the intersection? Well, it's only this part here, right? And this is the same as that, so the sets are equal. Thank you very much. See you next time. Bye-bye.